Okay, on to the final page of the quantitative chemistry questions. You've got quite a long question here about iron. So iron has a relative atomic mass of 56 and is found in many different compounds and ores. First point, what is meant by the term relative atomic mass? If you remember, that's a quite long, annoying definition you got in your notes. Not going to write it all out, I'll just show it to you here. Mass of an atom compared to the carbon-12 isotope, which is a mass of exactly 12. So as it is quite long and annoying, it does always give you a couple marks at least, so it's worth learning off really well. Part 2. Fe3 brackets CO 12 times is a compound which contains iron. It doesn't look like a particularly realistic formula, but you just have to go with it. 3 irons and 12 COs. What is the empirical formula of this compound? That's quite a hard formula question. Remember, empirical formula is the simplest ratio. So what basically you do is count up the total numbers of each element in that compound and then cancel it down to the simplest ratio. What's tricky is that the COs are in brackets, but again, don't get confused with that. All that means is you've got 3 irons, you've got 12 carbons, because that's the brackets, the 12 goes around the carbon as well, and 12 oxygens. If you write out like that, but it looks a little bit more simple, I can cancel that down by dividing everything by 3, which would give me Fe, just by itself. 12 divided by 3 is 4, so 4 carbons and 4 oxygens for that one. Part 3, 1 mole of hydrated iron sulfate contains 7 moles of ore of crystallization. Write the formula of hydrated iron sulfate. Again, just trying to make sure you understand what that terminology means. Remember, the moles of ore crystallization is shown by the wee number after the dot in the formula. So iron sulfate, again, I'd have to do a wee swap and drop Fe2 plus because it's iron 2, sulfate SO4 2 minus. Hopefully you can see from that it's just going to cancel out to be 1 of each. So it becomes FeSO4 dot 7H2O for that one. Part 4, calculate the percentage of ore crystallization present in hydrated iron sulfate. So you've got its formula. I just have to work out of that total mass how much of it comes from the water. So we've done that one before, or a question like it. FeSO4 dot 7H2O, need to work out the total mass. It's a wee bit of calculator work. All the masses are there, just add them up carefully. So that should end up with 278. The mass from 7 waters is going to be, again, I can't do it on my head, it's just going to be 7 times 18 because the mass of 1 water is 18 and there's 7 of them. The equation or calculation therefore becomes 7 times 18 over the total mass, which is 278, times by 100 to make a percentage, ends up with 45.3%. Again, if I don't tell you, 1 decimal place is a fair kind of number to give it to. Part B, we're actually going back to reacting mass questions here, something from the start of the booklet. Give you an equation, wants you to calculate the mass of iron in tonnes that can be attained from 16,000 kilograms of Fe2O3 reacting with excess carbon monoxide. So they're making this tricky for you just because they're giving you a huge mass of it, but that doesn't necessarily change the calculation. So we could lay this out by table method, but I've not got a huge amount of room, so I'm going to do it without the table method, just do with moles and ratios. So what it tells me about is the iron oxide. It tells me I've got 16,000 kilograms of it. Now, one wee complicated thing about the moles equation, moles equals mass over RFM, you might remember that the mass has to be in grams for it. That's not in grams. To turn the number of kilograms into grams, you need to times by 1,000. So the number of moles actually becomes on the top line of that. It's going to be 16 million grams. Again, that sounds scary. Well, maybe it doesn't, I don't know. But it's just a number, just a large number of grams. Have to divide by the RFM. Iron, 2 irons and 3 oxygens, add that all together ends up being 160. Again, you might see that looks quite nice. It's probably good because you've done it right. Those numbers will cancel down a wee bit. That gives you, make sure you get the correct number of zeros, it's 100,000 moles of it. Okay. So 100,000 moles of FeCO3. I want to work out the mass of iron it's going to make. Going to involve using my ratio. You'll notice here there's no number in front of the FeCO3, there's a 2 in front of the Fe. It's a 1:2 ratio to get to the iron with your mole ratio. Therefore, the iron, you're going to have 200,000 moles of iron. Last step is converting back into mass. Need to do a rearrangement here. Mass equals moles times RFM. Moles are already got 200,000. RFM is just the mass of the iron, which is 56, which gives you a final answer of, well, it'll be 11 million, I'll write it out, 11 million grams. To convert back into kilograms, so divide that by 1,000. No, in fact, I need to go double check this. I think I've done that wrong. So 200,000 times by 56. I think I've got one too many zeros there, sorry, yeah. Divide by that by 1,000 to get back into kilograms. Gives me 11200 kilograms. So again, dividing by 1,000. And I need to get into tons, which makes it trickier as well. Divide by 1,000 again to get kilograms into tons. So you get my final answer of 11.2 tons. So a lot of working out there with the units there, but the calculation itself with the moles is just a straightforward one. Calculate the percentage yield of this reaction if 10.2 tons of iron are obtained. Again, we exam tip, if you got this one horribly wrong in the exam, you can't get full 3 marks. So I would just make up a mass of tons for this answer if you get stuck that's bigger than the actual yield, and that'll give you 2 marks just by that. So remember, percentage yield equals actual yield over theoretical yield times by 100. The actual yield in the actual experiment is what's obtained, that's 10.2 tons. Again, doesn't matter what the units are as long as the units are the same, so 10.2 is actually fine to go in here. The theoretical yield predicted by the calculation is 11.2. Times by 100 make a percent, and then plug it in calculator, gets you 91.1% for your percentage yield there. Part C, this question goes on. Iron pyrite is another ore of iron, contains 46.5% iron and 53.5% sulfur. Determine the empirical formula. So by now we've done quite a few of those. We're trying to get the ratio of iron to sulfur. The first thing we work out is the grams. Now remember, percentages I can just treat like grams as long as I assume it's going to be 100 grams of the compound, because that would make it 46.5 grams of iron and 53.5 grams of sulfur. To convert that into moles, I need to divide them by their RFM, or in this case their atomic masses. Handily gives you them at the start of the question. 56 for the iron and 32 for the sulfur. Gives you moles of 0.83 to 1.67. So as I was saying, this one of the examples where you've got not a nice ratio, so it might be hard to see just straight away what the ratio is between these two. Again, if in doubt, divide by the smaller one. So if you divide both those numbers by 0.83, it actually comes out quite nice. It's 1 to 2 ratio. The final answer is the empirical formula, so that's the number of moles of iron to number of moles of sulfur. The final formula is FeS2. So final 2 questions. We've got a strange table question here. Gives you details of 3 calcium compounds, have fill in some relative formula masses and moles. So it's trying to show that you can work out between masses, moles and RFMs. So first thing I can fill out probably is the RFM column, because it's all empty and I've got all these different formulas. Some of them are quite tricky. So the first one's not too bad. 1 calcium, 2 oxygens, 2 hydrogens gets you 74. This one again, not too bad either. 1 calcium, 2 hydrogens, 2 carbons and 6 oxygens gives you 162. This one, sorry, 162, that is not 167. This one looks absolutely horrific. But again, just trust your calculator. So there's 2 17s, so that's 34 carbons. There's going to be 70 hydrogens. A sneaky second 2 carbons. Don't worry about the way they're split up. That's something you look at in year 12. So we're up to, I think, 36 carbons. There's therefore 4 oxygens and then a calcium at the end. So it looks horrible, but you just have to kind of double check it a couple of times. It should come out as being 606 though, once you add all those masses up. Once you've got that, if you look sort of left to right along each row here, you've got the RFM, you've got the mass of the substance. So moles equals mass over RFM. So calculated work comes out as being 0.0025. With this one, you've got missing mass, you've got the RFM, you've got the moles. Mass equals number of moles times RFM, which gives you 162 times 20. That's going to give you 3,240 grams. You have to make it into kilograms though, so 3.24 kilograms. Final one, again, similar question. You've got 600 grams, you've got moles 1.5, mass equals moles times RFM, which gives you 909 grams. Final question, I think is quite a tricky one. Calculate the loss of mass when all the water of crystallization is removed from 1.095 grams of hydrated calcium chloride. So what you actually think this is when you first look at it is it's a water of crystallization question. However, it can't really be a calculation for that one because they already give you the number of waters of crystallization. That's normally what you're trying to work out here. What this basically is, it's a standard kind of mole or like reacting mass question because they gave you an equation and they give you a mass and you're trying to out the mass of the other thing. So it's basically applying what you know about normal mole questions to like a slightly unusual equation, but just trust that equation. So I started by looking at the number of moles of the hydrated calcium chloride I've got first, which is that one. I've got 1.095 grams. So for the calcium chloride, so apologies that I spilled this working out into this question. So CaCl2.6H2O, the number of moles is, you have to cramp this in a wee bit, mass over RFM. A bit of careful working out gives you 219 for the RFM of that, and that gives you 0.005 moles. For the calcium chloride itself, so let me explain this step a wee bit closely, I'm asked to work out the loss in mass when all the water of crystallization is removed. It's got lighter because you remove the water, so one approach to this would be, if I work out the mass of the calcium chloride at the end, that will tell me how much lighter it's got. So if I treat like a ratio from this going to this, that'll allow me to get the mass of the product, like a normal moles kind of reacting mass question. So it's a 1-to-1 ratio. I know it's a bit silly kind of talking like that, but if you look at big numbers here, there's no balancing number there, no balancing number there. So 1 mole of this makes 1 mole of this. So therefore I will have 0.05 moles of calcium chloride at the end, which is what you probably would expect. I need to get back into a mass though. So mass equals moles times RFM. So 0.005 times by the RFM of calcium chloride, which again is going to be a wee bit of calculating to work it out. 111. 1 calcium and 2 chlorines. If you do a calculation, you end up with 0.555 grams. So once you got to that point, again, you feel most is working out here. You know how much of the hydrated calcium chloride you had at the start, 1.095 grams of it. You know how much it weighs at the end, 0.55 grams to that, because you worked out the mass of that, which is minus the waters. I just need to subtract the two. So the loss of mass will just be the 1.095 grams minus 0.555 grams. And that will be, if you do it in your calculator, 0.54 grams there. So tricky, kind of strange question. Final one is a bit more straightforward. You have to work out the percentage of the water of crystallization within that total mass. We've done plenty of those before. The whole formula is this. Add all those masses together. 1 calcium, 2 chlorine, 6 waters ends up being 219. If you add up the mass of the waters, that's 6 H2Os, 6 times 18 is actually 108. Putting those together, it's the waters, 108, divided by the mass of the whole thing, 219, times by 100, gives you a final percentage of 49.3%.